All right, welcome everybody to lecture 4 of Intro to Space Navigation. So we just went through kind of a late start today because we did a warm-up going over building a topocentric reference frame from latitude and longitude, which I think is a good exercise. But it's basically the same idea as the example from last class, building an LVLH frame. Right? If you've got your position, then you can kind of cheat. One of your vectors is along the position vector, so either normalize or negative and then normalize. You'll get one of your vectors from a cross product of a global frame vector and one of the vectors you've already built. And then the third one just completes the right-handed system. So if anybody needs any help with that, you can chat with me later, but hopefully you can see how the same content can be used to build a topocentric frame. So moving on, today we're going to be continuing our discussion of attitude representation. We're going to go over some of the fancier methods of attitude representation. So there's 4 that roll back to yesterday. We're going to talk about the attitude transformation matrix, otherwise known as a direction cosine matrix, or DCM. And then we also talked about Euler angles, so like roll, pitch, yaw, rotation sequences, right? So we talked about those last class. So today we're going to talk about angle vectors, sometimes referred to as Euler axis, Euler angles, which not to be confused with Euler angles. Leonhard Euler did too much stuff in his lifetime. It's like, I think there was a joke that, what is it, every equation needs to be named after the second person who found it, because otherwise it would all just be called Euler's equation. And we will be mentioning Leonhard Euler in the angle vectors lecture, and then also in the quaternions part as well. So going to be some fun. So I want to talk about those. Attitude transformation matrix is 9 numbers stacked in a 3x3 matrix, which describes the mapping from one frame to another. Angles is a set of angles with a kind of implicit assumption on the structure. If you and I both work at an engineering firm and we know that yaw, pitch, roll angles means yaw and then pitch and then roll, then we can use them, but you need to be really careful to make sure everybody's on the same page. And so the next thing we'll discuss is angle vectors. Also, one of the shortcomings of any 3-axis attitude representation, which is singularities, otherwise known as gimbal lock. We'll talk about that today. So let's see. I'm going to bounce around in my notes here today. Start with angle vectors. So I said something last class, which the astute among you might remember, that whenever you translate from one frame to another frame, there's always going to be one axis that didn't move, right? There's always going to be, if you rotate about the x-axis, then the x-axis is the same in both frames. We saw that all the way back here. Here it is, right? The E3 axis and the U3 axis are the same thing. The axis of rotation does not change. Now, even if it was a more complicated thing, even if it was a 15-degree yaw followed by a 30-degree pitch followed by a 45-degree roll, you would see frames where after the dust had settled, there's one axis in 3D space that didn't rotate between the initial orientation and the final orientation. So someone really smart who lived a long time ago already thought of this, and you'll never guess what his name is. So this lecture is angle vectors. And we're going to start by talking about Euler's theorem. This is Euler's theorem, not to be confused with Euler's equation, which we're going to need in a minute, but one thing at a time. Euler's theorem states that any 3D rotation can be expressed as a single rotation. So there's one axis that doesn't move about a fixed axis. Here's, let me move this. A single rotation about a fixed axis by some angle. So even after your yaw, pitch, roll sequence, your final attitude is related to your initial attitude by a single rotation about some axis. Now that axis could be really weird. It doesn't need to be the x-axis or the y-axis or the z-axis. It could be some weird linear combination of the three. But there is one axis that doesn't rotate. So by necessity, points lying along this axis will have the same value in the initial and final frames. Also, if I do say so myself, I think my handwriting is getting a little bit better, maybe just a little bit. It's certainly not quite as annoying to use the drawing tablet. So let's go through the exercise of proving this. Okay, so let's say we've got an attitude transformation matrix T. Well, let's remember a few things. The determinant of an attitude transformation matrix is 1. Right? That means that a vector that's multiplied by the attitude transformation matrix is not stretched or scaled, it is only rotated. Okay. We also know that the inverse of an attitude transformation matrix is the same as the transpose of an attitude transformation matrix because it is orthonormal. And we also know, and this just kind of makes sense based on the first two, that the determinant of the inverse of the matrix is the same as the determinant of the transpose of the matrix, and it's just 1. You can take the matrix, you can invert it, you can transpose it, whatever you do, it still has the determinant of 1. Okay, so here we go. We're going to start by saying that the determinant of T, which is 1, well, let's start with this. 1 minus 1 equals 0. Okay, the determinant of T is 1. The determinant of the identity matrix, I, is also 1, right? Because when you take I, you multiply a vector by I, you get the original vector. So not only is it not stretched, but it's also not rotated. It's completely untouched. So it had better have a determinant of 1. So determinant of any attitude transformation matrix minus the determinant of the 3x3 identity matrix is 0. Okay, now comes the party trick. We're going to do a whole bunch of steps, and each of these is a legal move. And then when we're done, you see something really neat. So you can rewrite this as the determinant of T minus I. Still 0. Still allowed to do that. You could also say that this is the determinant of T minus I transpose, right? Because taking the transpose of a vector does not change its determinant. Okay, so then if you go through and distribute this, that's the determinant of T transpose minus I transpose. But of course, the identity matrix, when you transpose it, it doesn't change. So that's just this. Okay. And so from here, remember that T transpose is T inverse. So I'm going to write this as T inverse. And I'm also going to write the identity matrix as T inverse T. Right? If you take really any matrix, multiply it by its inverse, you get identity. But certainly the case for an attitude transformation matrix. So still 0. All right. Now we're going to go through and do some distribution or some grouping of terms. So this is really T inverse times the identity matrix minus T, which is 0. And we can actually split this up. This is the determinant of T inverse times the determinant of I minus T. But we know that the determinant of T inverse is 1. So really what we're saying is that the determinant of I minus T is 0. Okay, well now here's something neat. We just said that the determinant of T minus I is 0, but also that the determinant of I minus T is 0. Okay, and whenever that's true, so determinant of t minus I equals the determinant of I minus t equals 0, this is the characteristic equation for a matrix with an eigenvalue of 1. So there are, of course, 3 eigenvalues. One of them has to be 1 in this case, just because this is the characteristic equation. We can kind of prove to ourselves if you were to do eigendecomposition on an attitude transformation matrix, it would have at least one eigenvalue that was 1. So hopefully that makes some sense. And of course, that is actually kind of jumping ahead. If you just imagine an attitude transformation matrix acting on a vector, right, then there's going to be, or acting on a whole series of vectors, acting on a whole space, right, moving from one frame to another, there's going to be one axis that is untouched by that rotation. And so the axis that corresponds to that eigenvalue of 1 is the rotation axis. That's basically where we're going now. So let E be the eigenvector of T corresponding to lambda's 1. And of course, we know the equation. When we're going to start doing eigendecomposition, we see something like this, right? A matrix acting on this particular vector is the same thing as the vector scaled. But because we're talking about the eigenvalue 1, the matrix acting on this vector is just the vector itself. So E has to be that rotation axis that we've been talking about since the start of our discussion. There's some axis that's untouched by this rotation. And you can just look at it this way. The axis multiplied by t is unchanged. Okay. Let's bring it in for a landing here. Thus, E must be the fixed axis of rotation that is untouched by t. All right. So that just proves to us that there is such a thing as this untouched axis. And now we're going to go through, and without derivation, just going to go through and describe how you can take an attitude transformation matrix and convert back and forth between that and the Euler axis, Euler angle. So,
can I ask a question?
Yeah, sure.
In the second step, like that t minus that identity equal to 0, then we get like that parenthesis t minus identity equal to 0.
Mm-hmm.
Is it that our assumption? Because I think, as I am correct, this determinant operation cannot hold to like minus put to the parenthesis, but I am not sure. Is it assumption or how we get sure that it will be hold always equal to 0?
I could be mistaken. I mean, maybe I'm rusty in my linear algebra, but I'm pretty sure that the determinant operation holds under subtraction and addition and stuff like that. Because you could think of it as you're performing the matrix operation T. I'm trying to think about how that would work. So if you're saying that you're taking some vector A and you're multiplying it by T, and then you're subtracting A, well, that's the same thing as TA minus IA, which is the same thing as T minus I times A. And the idea here is that t minus I can be treated as a single operation or a single matrix, such that the determinant of this combined, basically the way that the final vector is treated in terms of the scaling is the same whether you take it bit by bit or take it all together like that. So I'm pretty sure that's a legal move. But if I mess something up, then we can definitely go back and revisit that.
Okay, thank you.
Yeah. All right. An attitude can be expressed, where am I? Oh yes, by an Euler axis E and an Euler angle theta. Without proof, here is how to convert between an attitude transformation matrix and E theta. Theta, if you're starting with T, is the arc cosine of the trace of the matrix minus 1 over 2, where TR is the matrix trace operation, which is just some diagonal elements. And E is 1 over 2 sine theta T23 minus T32 T31 minus T13 T12 minus T21, where T can be broken down into elements T11, T12, T13, T21, T22, T23, T31, T32, T33. 1, 2, 2, 1, 3, 1, 1, 3, 2, 3, 3, 2. Good. So those are the equations to go from T to theta and E. Now, of course, you could also find E by eigendecomposition. We're not doing that. Now, if you want to go the other way, T is equal to the cosine of theta times the identity matrix plus 1 minus cosine theta times the vector E multiplied by itself transpose minus sine theta times the E cross product matrix, where in this case, just in it, actually in any case here, if you have a vector A raised to the power cross multiplied by B, that's the same thing as A, write A the same way twice so I'm not annoying, A cross B. So all we're doing is we're taking the cross product operation and basically restructuring the vector into a matrix so that A crossed B is the same as this matrix A to the power cross B. You could think of it this way. A cross is a skew symmetric matrix. So negative A3, A2, negative A1, zeros along the diagonal, positive A3, negative A2, positive A1. So these equations, these are crib sheet equations if we had crib sheets in this class. This allows you to go from an axis and an angle to T, or from T to an axis and an angle. And this is definitely going to come up on a homework assignment. Now, we can actually express theta and E just slightly more compactly. So the Euler axis and Euler angle represent four numbers with 3 degrees of freedom and 1 constraint, right? We know that E is a unit vector. Okay, we can store this information more compactly by multiplying them to get an angle vector. And that's simply the angle vector, which I'm going to write as phi, is just theta E. So you could think of it this way. If you've got this angle vector, if someone says, hey, here's the angle vector that describes the rotation from this frame to this frame, you'd say, okay, great, you've given me 3 numbers, but I know that it's an axis multiplied by an angle. So theta has to be the norm of the angle vector. And then E has to be the angle vector normalized, which I like to use the shorthand left bracket, right bracket to mean normalized. If I get a little lazy and I don't feel like writing that. So E is the angle vector normalized, theta is the norm of the angle vector. And if you want to, we can also say that T is the exponential function applied to the cross product matrix made out of this angle vector. Or you might see this written as e to the power theta cross. This is mathematically true, but this is rarely done in practice. So generally, if I see somebody starting with an angle vector and converting to an attitude transformation matrix, I see them extract the angle and the axis using these equations and then popping those into this equation right there, which is definitely one of the more important equations in these lectures. So that is an angle vector. There's 3 numbers which describe a rotation from one frame to another. Angle vectors. So far, so good. All right. Now I want to go back. We're done talking about 3 axis or 3 degree of freedom attitude representation. So that was the Euler angles, roll, pitch, and yaw, and then the angle vectors. Now there's a shortcoming inherent in those, which some of you might have heard of before. If anybody's ever heard the phrase gimbal lock before, that's what we're about to talk about next. And it's something that happens with any 3-axis or 3-component representation. So next we're going to talk about singularities and gimbal lock. So Euler angles, so roll, pitch, yaw, make intuitive sense. At least I think so. And are often one of the first methods of attitude representation taught to beginners. But they have a dark side. Just in general, special order 3, an attitude transformation matrix, or any 3-axis or 3-component. Let's think about it this way. SO3, so a rotation in 3D space has no global 3-parameter representation. Without singular points. In plain English, whenever you choose a 3-component attitude representation, you're dancing with gimbal lock, which is a phrase that I borrow from the movie Apollo 13. So if anybody's seen Apollo 13, phenomenal movie. Definitely one of the movies that made me want to work at NASA in the first place. There's a part in the movie where they're trying to do a burn manually, and their attitude was way too close to the gimbal lock attitude. So because of the way that the spacecraft was built and because of the way that it used an actual physical gimbal with like rotating rings for attitude determination, there was a orientation in 3D space that it just couldn't go to without physically damaging the gimbal, or not necessarily damaging, but without hindering the performance of the gimbal. So they just don't point the spacecraft that way. It's okay to point it any other way. But the burn that they had to maneuver to kind of get back onto a free return trajectory with Earth was close enough to gimbal lock that they were in serious trouble of having that issue. And gimbal lock is, well, it's a bad day under the best of circumstances, but it could have killed them on Apollo 13. So what does gimbal lock mean? Well, let me start by asking you this question. If a person is standing at the North Pole, like Santa, for example, what is their longitude? Right. So the way that we have our kind of map of the world set up, we've got lines of longitude, lines of latitude. There are singular points at the North Pole and the South Pole where longitude starts to not really make any sense anymore. When you're close enough to the North Pole, longitude, it just doesn't really mean anything. You're, instantaneously at every position in terms of longitude if you're at the North Pole. And so if you're trying to say, okay, go to 90 degrees north, 45 degrees west, then you can do that. But if you're at the North Pole and I say, well, what is your longitude? You say, I can't really even answer that question. That doesn't even mean anything. Right? The problem is that this can actually happen with Euler angles. You can get into this situation where your angles have been coupled and it becomes impossible to extract your attitude from the actual reading of your angles of your instrument. Right? And that is referred to as a singularity. So attitude singularities can occur mathematically or physically. Okay, so a spacecraft has a 3-axis gimbal used to measure its attitude with respect to inertial space. Okay. So the gimbal, you can think of it like this. You've got some base, and you've got some ring which is allowed to rotate. And then mounted inside that is some other ring which is allowed to rotate. So here's your first axis of rotation. Here's your second axis of rotation. And then that axis of rotation moves. And then suppose that there's also a third axis of rotation, which is this way, which also moves. Right? So you've got a 3-ring gimbal. Further, suppose axis 3 has become aligned with axis 2, or sorry, with axis 1. This happens whenever theta 2 is 90 degrees. So whenever the second ring, so first rotation, second rotation, if the second rotation is exactly 90 degrees, then actually you get the situation which is more or less, well, not exactly as drawn. If theta 2 is exactly 90 degrees, then this axis here, sorry, I'm drawing arrows, 2 arrows right now, so just kind of use your imagination, would become aligned with the first axis. In that circumstance, either a rotation about the first or the third axis would look the same to whatever object you have on the inside. Right, so you would not be able to tell, am I rotating about axis 1, or am I rotating about axis 3? It's impossible to answer that question because it's the same axis. So in this circumstance, a rotation about either axis produces the same motion. Therefore, one cannot uniquely know theta 1 and theta 3. So in this circuit, physically stuck. You're going to need to reach in with your hand and spin it around because you're not going to be able to get it fixed without some manual intervention. What we could also do, let's see what happens to, remember the really big, nasty attitude transformation matrix, T, A, B, C, T corresponding to a yaw, pitch, roll sequence, this guy here. Here, actually, borrow this. Let's see what happens to T, pitch, and then roll when yaw is 90 degrees. So just as a reminder, there's original what we get, T, Z, Y, X corresponding to gimbal lock is what? Well, let's think about it. We've got the cosine of 1, the cosine of 2. The cosine of 90 degrees is 0. So the top left element is 0. And then the top middle element is also going to be 0. We've got cosine of 2. All the cosine of 2 terms drop to 0. The sine of 2 is going to be negative 1. This is going to be 0. This is going to be 0. And then this is going to give us, remember, sine of 2 is going to be 1. Cosine of 2 is going to be 0. So you can just go through and make some simplifications. And what we're going to see is cosine 1 sine 3 minus cosine 3 sine 1. Cosine 1 cosine 3 plus sine 1 sine 3. Sine 1 sine 3 minus cosine 1 cosine 3, and cosine 3 sine 1 minus cosine 1 sine 3. And what we're going to see is this is a singular matrix. So a singular matrix means what? It is rank deficient, or it is not invertible. Well, now we've done something wrong if our matrix is not invertible, right? Because isn't the whole point that the inverse of an attitude transformation matrix is just the rotation that undoes that attitude transformation matrix? Well, basically, gimbal lock is a rotation that can't be undone. And in this case, it is a physical problem with the gimbal, but it is also a mathematical problem with our construct that we've used to describe the motion of the gimbal. So what I find interesting is that the physical problem and the mathematical problem happen at the exact same orientation, which I suppose makes sense. But in this circumstance, it is impossible to recover theta 1, theta 2, theta 3. So gimbal lock is bad news. So what do we do about that? Stay away from attitudes that cause gimbal lock. That's one option. Or don't use Euler angles. That's another option. And you might say, okay, well, isn't the same thing going to happen if I use an angled vector? It's like, yeah, it will. Any 3-parameter representation is going to have this issue. So what do we do instead? Well, there is another player that we're going to talk to called quaternions. But I think we've reached a good pausing point. I want to give everybody about a 10-minute break, and then we're going to come back and talk about quaternions. Any questions about the stuff we've covered so far, or we're good to take a break? All right, cool. Let's say take a break and come back. See, it's about to be 6 for me, so it's about to be 7 for you. So 7:08. All right, time to get back. So, welcome back, everyone. Looking forward to talking about what I think is the coolest. I mean, realistically, what you'll probably use the most in this class is the attitude transformation matrices, but quaternions are just fun. So I want to next. So some of you might have heard of quaternions before, some of you might not have. I'm going to start from zero, assuming nobody has any idea what I'm talking about. So quaternions. Quaternions are an elegant, compact way of describing 3D rotations using 4-dimensional complex numbers. To get an intuition, we'll start with a 2D example. So for those of you that are watching my last year, this is where I kind of start to deviate. Last year, my discussion of quaternions was, I think I could have done better. So this is my attempt at improving on that. I really want to make the beauty and the elegance of quaternions clear. So hopefully I can accomplish that. And one of the things that really helped it click for me, well, a couple of things, was seeing an example of a complex 2D rotation, which is relatively simple to get a hold of in your mind, and then seeing how that scales up to 3D. And then also I went back and I rewatched, for those of you that are familiar, there's a YouTube channel called 3 Blue 1 Brown, which has like 3 different videos on quaternions. And I went back and I rewatched those. A lot of things started to click in a way that they didn't before. So I'm going to post the links to those videos when I post the information about this lecture on LMS. Definitely recommend you go check them out. There's one in particular that's only 5 minutes long that kind of encapsulates what it takes me 30 minutes to say. I think his name is Grant from 3 Blue 1 Brown, can do it in 5 minutes with cool animation. So go check it out. But here's the example. 2D complex rotation. A 2D rotation can be expressed as a point on the unit circle in the complex plane. So just think about that for a little bit. If you've got, say this is the complex plane, this is the real axis, this is the imaginary axis, then any vector on this unit circle, or any point on this unit circle, would be, so for example, about right here. Let's say this angle is theta. Then this distance here, this distance here, is sine of theta. This distance here is the cosine of theta. So this point is going to be what? Cosine of theta in the real direction plus sine of theta in the imaginary direction. So multiply that by the I vector. You might be familiar that this is the same thing as e to the power I theta, or the exponent I theta. And this is Euler's formula. There he is again. I promise we're going to talk about at least one mathematician today who wasn't Leonhard Euler. So what we can do is we can describe, for example, a 45-degree rotation by the exponential function evaluated at I to the power pi over 4. Sorry, my handwriting is dropping off here. Let me try this again. Now, I like to use the exponential function rather than e to the power of, because e to the power of a complex number starts to really not make sense anymore. But the exponential function, which of course the exponential function evaluated at 1 is just e, right? That just makes more intuitive sense to me, at least. So we can describe a 45-degree rotation by the exponential function evaluated at I to the power, or sorry, evaluated at I multiplied by pi over 4. So suppose we'll to rotate the vector two plus 0i, so just the number 2 on the real number line, by 45 degrees. Well, what do? We just multiply it out. Okay, so intuition would tell us, right? What should we get when we multiply, when we rotate the vector 2 by 45 degrees? Well, I'll just draw a quick sketch here. Here's the unit circle. Suppose we've got a vector that's out here, so it points from 0 to 2. If we rotate it 45 degrees, it's going to be up here, which is to say it's just the point on the unit vector scaled by 2, like the rotation point on the unit vector scaled by 2, or you could think of it as rotating up this way. And intuition tells us, hopefully this makes sense if we just stop and think about it. The answer will be root 2 in the real direction plus root 2 in the imaginary direction. But let's just prove that to ourselves. Okay. What is 2 times cosine theta plus I sine theta? Or in this case, cosine of pi over 4 plus I sine of pi over 4. Well, that's the same thing as 2. What is the cosine of 45 degrees? Well, it's root 2 over 2 plus I root 2 over 2. Cancel, cancel, cancel. You get root 2 plus I root 2. Okay. You could also do it the hard way. What is 2 times the exponential function evaluated at I, or not I theta, I pi over 4? Well, just a reminder that the exponential function, I'll write it over here. Exponential function just of x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus so on and so forth. Or you could think of it as the sum of all numbers. We'll use n equals 0 to infinity of x to the n over n factorial. And if you plug in 1, so what is 1 plus 1 plus 1 squared over 2 plus 1 cubed over 6 plus so on and so forth, you get e. That's where Euler's number comes from. But the exponential function is more fundamental than, I'm sorry, is it feeling dumb right now? Yeah, it's 1, it's not 0. The exponential function evaluated at 1 is Euler's number, e, so that's where that comes from. But the exponential function is more fundamental than the exponential number. So 2 exp of I pi over 4, what's that going to work out to? Well, that's going to be 2, and then we're going to start a big curly bracket. 1 plus I pi over 4 plus I squared pi over 4 squared over 2 plus I cubed pi over 4 cubed over 6 plus I to the 4th pi over 4 to the 4th over 24. And then we're just going to drop it there for now. That's enough terms. So this equals what? It equals 2 times 1 plus I pi over 4. But I squared is just negative 1. So this ends up being minus 1/2 pi over 4 squared. I cubed is negative I. So this ends up being minus I over 6 pi over 4 cubed. And then I to the 4th is just 1 again, right? So this is 1 over 24 pi over 4 4th power. And this is where I'll let you go and work this out on your own, but you end up with getting root 2 plus I root 2 again, which should be the case if Leonard Euler is correct. And Leonard Euler is usually correct. So to summarize, the exponential function evaluated at I times theta marches along the unit circle by theta radians. So a couple of things. This is a compact way of describing a 2D rotation. So you don't need a whole 2x2 attitude transformation matrix, which you could have done. Not necessary, just exponential function of I theta. This is also why, for those of you that have been thinking about this, you might have heard that e to the I pi is negative 1. Right? So if you start at 1 and you march around the outside by pi radians, you end up over here at negative 1. Right? So e to the I pi just means a 180-degree rotation in the complex plane, which is the same thing as just taking a number along the real line and then negating it. And so those of you that have seen that, hopefully that makes more intuitive sense now. So now take note. A 1 degree of freedom rotation requires a 2D plane to describe. Therefore, a 3 degree of freedom rotation requires a 4D hyperspace to describe. So we're going to hyperspace. So does this 2D example make sense? Because it's about to get a lot spicier. So I'm hoping that we're really rock solid on this. All right, I'll take silence as a good sign. So going back to our discussion, quaternions. Quaternions were discovered in 1843 by, not Leonard Euler, by William Rowan Hamilton. So what Hamilton was after was a set of numbers that is basically the complex numbers. So I, a real number plus some number times I. He wanted to take that from 2 dimensions to 3 dimensions and have it make sense, have there be a system of multiplication and division, multiplication that actually makes sense in 3 dimensions. And he spent a long time trying to do it. And one day it came to him in a flash of insight. And there's this famous story that he was walking across a bridge, and when it came to him, he didn't have a scrap of paper. So he chiseled the equations into the bridge, which seems to me that you just run home and go write it down. But it makes for a great story, and maybe that's true. There is a bridge that has this number chiseled, or this equation chiseled into it. Hamilton figured out that you can't go from complex numbers in 2D to complex numbers in 3D, but you can skip and go to complex numbers in 4D, and it actually works out really beautifully. So quaternions are a 4-dimensional complex number system with one real dimension and 3 complex dimensions. So you've got the I-axis, but then you also have the J-axis, which is a different complex number than I, and then you've got the K-axis, which is a different complex number than J. And the way it works is that I squared is also J squared, is also K squared, is also I times J times K, and they're all -1. And also, if you have a vector in I times a vector in J, that is the same thing as -Ji, which is K. Jk is the same thing as -Kj, which is I. And then Ki is the same thing as -Ik, which equals J. And these relationships here look a little bit like X cross Y is Z, Y cross Z is X, Z cross X is Y, and then like hopefully that makes some sense. So actually, there's some really interesting relationships between this and then like kind of some of the vector techniques that we're used to. So I will mention that quaternions outside of this class, just on their own, quaternions are a rich and elegant part of mathematics. Go watch 3 Blue, 1 Brown. So in 2D complex rotation, a point, or sorry, in 2D complex numbers, misread my notes. A point on the unit circle describes a rotation. In 4D complex numbers, a point on the unit hypersphere describes a rotation. So before you get too spooked by that, in 2D space, a point on the unit circle is just a vector in 2D space with a norm of 1, right? All of the vectors in 2D with a norm of 1 lie on this circle. Well, all of the vectors in norm of 1 lie on a hypersphere. So before we get too spooked by complex numbers and hyperspheres, what we're talking about is a 4-dimensional vector, a 4-unit long vector with a norm of 1. Okay, well, that's not quite so scary. So aerospace engineers like us frequently use unit quaternions to describe vehicle attitude. All right, that's a lot of yapping. It's time for an equation. Q hat, so unit quaternion, can be broken down into a scalar part. Whoops, it's a scalar, and then I drew the hat on it, and a vector part. Or you could think of it as Q scalar, Q1, Q2, Q3. Now, this is where you got to be careful. Some people will say Q1, Q2, Q3, Q4, or Q0, Q1, Q2, Q3. So like everything, there's different conventions and different opinions about how we should be done. We're going to use the scalar first convention in this class, and I'm always going to call it Q scalar, so there's no ambiguity about which one is the scalar term. But this is just cosine of theta over 2, E1 sine of theta over 2, E2 sine of theta over 2, E3 sine of theta over 2, or cosine theta over 2 E sine theta over 2, if you wanted to write it a little bit more compactly. Do you see how that's the same familiar Euler axis and Euler angle from earlier this lecture? And so this gives us a scalar part and a vector part. And already you can see how you can build a quaternion from an axis and an angle. Okay, now just be careful. Some people use scalar last convention. Okay. Now, because of the unity norm constraint, a unit quaternion's inverse is its conjugate. What the heck does that mean? So Q, first of all, Q has a norm of 1. And similarly, Q inverse is the same thing as, the conjugate of Q.
Professor, could you just read that last line you wrote?
Because of the unity norm constraint, a unit quaternion's inverse is its conjugate.
Thank you.
Yeah. I'll try a little harder. This is just this, which is just Q scalar negative Q vector. So if you want to invert a quaternion, all you do is invert the Euler axis, which kind of makes sense, right? If you take your a rotation about some axis by some angle and you want to undo it, what you could do is you could negate theta, or you could negate E. Either one of those would get you back to this point, which is a negative sign on the vector term, an unchanged scalar term. That is the inverse of your quaternion. Hopefully that makes some intuitive sense. We've got 4 numbers and 1 constraint. So we've got 3 degrees of freedom. And what's really cool is quaternions are not susceptible to singularity. There's no way to get stuck in gimbal. Also, hopefully this makes some sense. Q and negative Q describe the same rotation. So you can just try that. If you take your Euler axis and negate it, and your Euler angle and negate it, so a negative theta rotation about negative E is the same thing as a positive theta rotation about positive E. But if you actually just pop that into your equations, negative theta, negative E, you get back to the same original quaternion. Or you could think of it as trying to get your quaternion out, like trying to extract an E and a theta from Q and negative Q, you're going to get the same thing. So sometimes people run into an issue where it's like, oh no, my quaternion is all negative. It's like, nope, don't panic, it's fine. So you could think of this as equivalent to rotating negative theta about negative E. we can convert from a quaternion to an attitude transformation matrix by T is equal to QS squared minus Q vector transpose Q vector times the identity matrix minus 2 Q scalar Q vector cross product matrix plus 2 Q vector transpose. So a lot of the time in aerospace engineering, we use quaternions as a storage method. So you take your attitude transformation matrix, you extract your axis and angle, and then you use that to build your unit quaternion. And now you're saving 4 numbers instead of 9 numbers. And then you can also take your quaternion, go from quaternion to axis angle to attitude transformation matrix, or you can go directly from quaternion to attitude transformation matrix. But quaternions are so much more than a storage device. They're a whole number system, and you can do math in quaternion space if you want to. So moving forward, this is optional. Never going to ask you to do this in this class. The worst I'll do is I'll give you a quaternion and not explain what to do with it, and you're meant to figure out, oh, turn that into an attitude transformation matrix. But there's some really cool stuff we can do with quaternions. Also, I'm keenly aware that we're a little bit over time today, so I want to wrap up in not too long. So we can use quaternion multiplication oh, sorry, misread my notes. We can use the quaternion multiplication operator when we have sequential rotations. But we must be careful of our conventions. So we use the non-Hamiltonian convention such that quaternion multiplication occurs right to left, just like matrix multiplication. So you can think of it as this. Let's say we've got quaternion A being multiplied by quaternion B. You could think of this as A happens to B. The same way that when you've got like, T times some vector, T happens to that vector, right? Same idea. The way we do quaternion multiplication, I mean, actually, we already defined quaternion. Of your scalar term as being your real axis, and then your vector term as being I, J, and K members. Just follow right here. I squared is J squared is K squared is IJK is -1. IJ gives you K, JK gives you I, KI gives you J. If you follow this convention, then you can just do all of your rotation or your multiplication. Or here is a shorthand way of doing it. Your scalar term is the scalar term of A times the scalar term of B minus the vector term of A transpose vector term of B. And then your vector term is scalar term of B times this vector term of A plus A scalar term, B vector term, minus A vector term crossed with B vector term. So this is a way shorter way. This is your scalar. This is your vector. So let's say you wanted to code up something in MATLAB or Python. Now, of course, there are also pre-coded MATLAB and Python functions that will do quaternion multiplication, but I highly recommend you code up your own because you'll know exactly what the convention is that it uses. This is how you would do quaternion multiplication. And almost done. So because we defined multiplication this way, then the attitude transformation matrix that you get from the quaternion that maps from A to C is the same as sequential rotations. Think of it as we've got a quaternion that goes from A to B and then one that goes from B to C. That's the same thing as T of Q B to C multiplied by T of Q A to B, which is the same as T B to C T A to B, which is the same as T A to C. Hopefully that makes sense. So at any given one of these steps, you can convert from quaternion to attitude transformation matrix. The same basic idea applies. I'm also going to retry drawing that letter B because that's one of my worst letter Bs. I can do better than that. So the point is, it is right to left multiplication. All right. Now, complete tangent, you may also benefit from knowing the quaternion kinematic equations. So we will not use these in this class, but one of you probably will use it for your research. But they are necessary for modeling attitude dynamics. So complete tangent, if this helps you, great. If not, ignore it. This is something that I used in my research at one point. Let's say you've got some cube floating in space, and it's got a body X direction, a body Y direction, and a body Z direction. It also has some rotation rate about the X, some rotation rate about the Y, and some rotation rate about the Z. So those are not angles, they're actually body rates. What we'd like to be able to do is describe how quaternions change over time if you know the angular velocity of your body. Now, all this stuff, angular velocity, dynamic modeling, we don't really do a lot of that in this class. Most of the time we're dealing with static problems. But if this helps, then Q scalar dot, Q1 dot, Q2 dot, Q3 dot. Make that more clear. That's a dot. Is related to your body rates by, let's think about it. If you've got omega X, omega Y, omega Z, these are body rates. There's going to need to be a 4x3 matrix that does this mapping. It works out to be negative Q1, negative Q2, negative Q3, Q scalar along the diagonal, and then negative Q3, Q2, negative Q1, positive Q3, negative Q2, positive Q1, which if you see that structure, it actually might look a little familiar. This is 1/2 negative Q vector transpose, and then this is Q scalar times the identity matrix minus Q vector cross product matrix multiplied by omega X, omega Y, and omega z. So hopefully that's helpful to somebody. Actually, I realize we've gone over time by about 20 minutes, which probably has to do with the fact that we started about 20 minutes late. So I'm going to pause here. Class is dismissed if you've got somewhere that you want to be. I have one more example that I'm going to burn through, and you're under no obligation to stick around and listen to it. I'll happily lecture to an empty room and then just record and post this later. But for those of you that want to stick around, we're going to do one numerical example with quaternions, and then we'll be all done. But if you got to go somewhere, then feel free to vamoose. So here comes an example. 4D complex rotation. And that just applies more generally. If I'm yapping too long, feel free to just leave and then watch the video later. Say, okay, but how do we actually use quaternions? This might feel kind of overwhelming. Learned a lot of new math today. So in practice, we would usually go from quaternion to a direction cosine matrix and then just use that. But you don't have to. I want to actually do two side-by-side examples and show you numerically that this will all work out. Suppose we want to rotate. Let's say we've got some vector p, and p is just 1, 2, 3. About some vector which is just, I want to take 1, 1, 1 and then normalize it by 45 degrees. Okay, what we're going to do is we're going to do that using a direction cosine matrix and using quaternions. So here's the DCM method, and then here's the quat method. So first of all, our Euler axis in this case, I'm just saying 1 in the x, 1 in the y, 1 in the z, scale that so it's a unit vector. What we end up getting is root 3 over 3, root 3 over 3, root 3 over 3. And I'm just writing this out sideways because I think it fits more neatly on the paper. And then theta is pi over 4. So there's another 45-degree rotation. Remember our equation to go from an axis and an angle to an attitude transformation matrix. This is going to be the cosine of pi over 4, which is root 2 over 2, times the identity matrix, plus 1 minus, oh, you know what? Do I have a mistake in my notes? Sorry, stand by for 1 second. This should be a cosine, I believe. Stand by. Sorry, I don't want to write something dumb on the video and then it gets recorded forever. It is cosine. Okay, yep. Made a mistake. I should say cosine. Okay. 1 minus cosine of pi over 4 times E transpose minus sine of pi over 4 E cross product matrix. And if you work this out, what you'll get is that T is 0.8047. You can do this on your own if you want to make sure I'm right. 0.5059, negative 0.3106. And as you might not be shocked, this is symmetric. 0.8047, 0.5059, 0.5059, negative 0.3106, and 0.8047. And so if you actually take T and multiply it by P, well, there's our rotation. And we get 0.8846 we get 2.8165, and we get 2.2989. Okay, who cares? Well, because now we're going to do quaternion math and show we get the same answer. Right? So in this case, our scalar term is the cosine of pi over 8. And our vector term is the sine of pi over 8 times root 3 over 3, root 3 over 3, root 3 over 3 transpose. Now here's the way we do quaternion. The new term, so I guess we'll call this P prime for now. P prime is not the quaternion multiplied by P. You actually need to make a sandwich out of it. So it's actually going to be Q quaternion multiplied by P, and then quaternion multiplied by Q inverse. Okay, so if we write that out, then it's going to look like this. Q is cosine pi over 8, and then it's going to be root 3 over 3 sine of pi over 8. And it's going to be the same all the way down. Root 3 over 3 sine of pi over 8. And root 3 over 3 sine of pi over 8. And if you take this, quaternion multiply it with P. Now, what is P in this case? Well, the best way to think about it as it's going to be 0 in the real direction, 1 in the I direction, 2 in the J direction, and 3 in the K direction. So that's P. And then we're going to quaternion multiply that with, I'm going to cheat because my hand's starting to cramp. Quaternion multiplied with the same thing, except remember, the quaternion inverse is you negate these 3 terms. So these all get a minus sign. And the first thing we would do is we would multiply these 2 quaternions together. Again, you can use the I, J, and K rules if you want to, or you can kind of code them up for yourself, or technique that I show up here. We multiply those together, and then we multiply these together, and I'll leave it as an exercise to the reader. But what you end up with is that P is 0 plus 0.8846I plus 2.8165J plus 2.2989K, which is the same thing. So all that to say, you can do these rotations in 4D space using quaternions, or you could treat quaternions as a container, which is just a neat way to store your axis and your angle that you know isn't going to be ambiguous later. It's up to you. And then just to zoom out even more, in the past 2 lectures, and they've been long ones, sorry about that, we've now gone over attitude transformation matrices, Euler axes, Euler angle. We've gone through Euler rotation sequences like pitch, yaw, and roll. And then we've talked about the unit quaternion and how those can all be used. And everything that we do in this class with regard to attitude or relative orientation uses one of these techniques. So thank you, everybody, for your patience and sticking around. And I'll be happy to stick around after the recording stops to answer any questions.